Hi everybody, welcome back to Chem 161. What do we got going on today? We have, oh yeah, right, it's chapter 3, surprising nobody. But don't despair just yet, because we're almost done with chapter 3. We might actually finish it on Tuesday. We'll definitely finish it next week. We're going to get a big chunk of it done today. Agenda items that are on the screen. Last call for lab worksheet number 3. It's due tonight. Get it in or else. Or else I don't grade it, really, is what it comes down to. In this section, what we're going to do is we're going to look at a new concept in quantum mechanics that is actually really important. In fact, if you could distill the entirety of quantum mechanics down into 2 topics, I would say that those 2 topics would be N, which is the principal quantum number, and Z effective, which is what we're going to talk about today. Everything in quantum mechanics is sort of just a sub-level of those 2 topics, I guess you could say. It's all based on that. N being the distance an electron is on average, and Z effective being how strong the pull from the nucleus is. So let's talk about what Z effective is and see how it governs some various trends that we observe here. So the first thing we're going to define is how big are atoms. Most of the time, when we're looking at matter, it's bonded to other atoms, or atoms are bonded to other atoms. And so it becomes really difficult or even not useful to find the radius of an atom. So we're going to define covalent radius, or also known as atomic radius, as whatever half the distance is between 2 bonded atoms, if those atoms are nonmetals, because it's very hard to get individual atoms and then measure them, because they just rebond to each other. Or the distance between the nuclei for 2 metals. For example, in a metallic compound, all of the atoms line up in a line. Their orbitals don't really overlap, so you can get their atomic radius much more easily. So a visual picture of that would be here. So this is bromine. Br2 forms a 2-atom molecule. But you can see if I continue this like dotted line right here. Oops, I kind of missed there, but that's okay. Part of the radius is kind of double counted. And so the radius that you would actually get for the atom would be quite a bit different than the bond distance that I'm showing there. And the reason that that overlap exists is because that's where the bonding electrons occur. We're going to talk about that more in chapter 4. But we need to define it in some manner, so this is the manner that we have chosen. So whatever the bond length is divided by 2, we're going to call the radius of our atom. If the atoms don't covalently bond, then it's just whatever its radius is, because we can measure that directly. Now, why are we defining that? Because we're going to explore how large atoms are relative to their atomic number. And it is actually not trivial to do that on the periodic table. You could look at the periodic table, and there are going to be a bunch of different trends. In fact, do I have a picture here? Yeah, I do. Here's the trend in atomic size, and you probably look at that and go like, wow, there's no pattern at all that I can observe. But it turns out that there totally are patterns. Because before we transition to the previous period, sorry, I'm trying to draw here and also explain. Before you transition to a new period, the atom is at its minimum size. So you can see that the noble gases here are at the very end of their row. And they are the smallest thing in a while. And then when you go to the next row, the size shoots up and then it starts shrinking again. And this pattern persists. So every noble gas is the smallest in its period. And then every alkali metal, which is the first one in its period, is the largest. And the size keeps going up and up and up and up and up and up and up. And if you look at it carefully, you could kind of say, oh, okay, well, this looks like this. What does this look like? Have we seen this before? I wonder. That's kind of interesting, right? What are the energy levels doing, or what are the radii doing? Well, they are cramming together just like the energy levels. So it turns out N is definitely involved. For sure. And then what is happening as we go across each period? Well, not only are the number of electrons increasing, but the number of protons is increasing. So the number of protons must be involved, because what would make an atom smaller? If the atomic radius is just defined as how big the electron cloud is, and protons are what are pulling on the electron cloud, then the protons must be what is influencing the size, right? So these two factors are involved by looking at the data on the screen here. Number of protons somehow, and then also the principal quantum number, how far away the electrons are allowed to go in their highest level energy orbital. So I'm going to go back to the previous slide here. And let's look at the major effects that have been stated in the chapter text. How many energy levels are filled with electrons? Yep, we know what that is. That is totally N. So N affects size, very obviously. The more electrons you have, the higher your N is, and the larger your atom is. Now, we have the second topic right here. We know what nuclear charge is, but what's the word effective mean? Nuclear charge is just how many protons there are. That would be Z. Remember when we described isotopes with Z and A? With atomic number and mass number in Unit 2? Yeah, we're going to come back to that idea. What the heck does that mean, though? We're going to talk about that in just a second. Now, if I ask you how the radius of an atom changes with increasing atomic number, then the question I am asking you is to describe what you see on this chart. How does atomic number affect atomic size? As atomic number increases, atoms tend to decrease in radius unless you jump down to the next period. That'd be a great answer. I'm saying how, so I want you to explain what the behavior is. Now, if I'm asking you why does this happen, then we need to go into more detail, right? And that's where N and Z effective come into play here. So let's introduce the fundamental property of charge. All charges are attracted to opposite charges. All charges are repelled to like charges. Because the nucleus is positive and electrons are negative, they are attracted to each other, and they follow Coulomb's law. All charged objects follow this equation. Here's the equation. Wait, Wes, I thought we weren't doing math anymore in this class. You're totally right, we're not. I'm not going to make you calculate the energy of this charge. I am going to put the constants on the screen here just so that I can scare you a little bit. We all know what pi is. Epsilon naught is the permittivity of vacuum. This is how effectively charge permeates through space. And we don't give a shit about it. We're going to ignore it. In fact, we're going to reduce this equation down to the following terms. Q1 times Q2 over R Now, what are these terms? Q is equal to the charge, and R is the radius, or distance. Now, what does this mean for us? Well, if we go over here to the PowerPoint, we'll put this equation on the screen just so we can look at it. And of course, PowerPoint breaks, or Photoshop breaks. What we can do, oops, not equals, but proportional to. What we can do is for each of these Q's, we can just substitute in whatever the charge is that we're looking at on our objects. And then R is just the distance between them. So, for example, if I had a proton and an electron, and they were some distance apart, and we don't even care about units, really, because we're going to all do this all abstractly, right? Then what the equation would look like would be something like this. And that's going to equal some energy of attraction between them, because my charges are opposite. Now, if I get a negative number, that represents an attractive force, because my oppositely charged objects will always generate a negative number when multiplied together, right? If I get a positive number, I get repulsion. And that would arise from if I had two positive things or two negative things, because a negative times a negative is a positive, yeah? So this is sort of how we're going to be using this equation. We're going to be using it conceptually. I'm just going to input the charges directly and then divide by the distance. And that's going to give me some number. I don't really care what that number is. What I do care about is if I change the circumstances relative to some other circumstance. So up here in the 50 distance case, I get some energy. But if I look at the same case in this distance, this number will be smaller because I'm dividing by a bigger number. Likewise, I could do a scenario like, say, this one. And then I put it in the equation and I get this. And then my energy increases because of the fact that I put a 2 here. It effectively doubled. So we're going to be looking at this equation conceptually. If I increase the charge relative to some default situation, what happens to my energy of attraction? If I increase the distance, what happens to my energy of attraction? Well, because the formula is Q1, Q2 over R, as we can see at the top of the screen here, or sort of top of the screen, increasing the amount of charge increases the energy, because that number is on the numerator. The distance, however, is on the denominator, so if I increase the distance, I decrease the energy of attraction. In other words, electrons that are further from the nucleus are less attracted to it. Okay, that's cool and all. How do we apply this information using actual atoms? This screen just describes what I was talking about before. Well, let's consider what an atom feels. Here's my nucleus, and I'm going to just do, like, I don't know, boron. I'm going to do something like this. In an atom, my electrons that are buzzing around the outside feel the following forces. There's always going to be an attraction to the nucleus. What other force is felt, though? Well, electrons repel each other, so they're going to be pushing each other away, like so. And these guys would push each other away, too. So the purple forces are all repulsions. Those electrons are pushing each other apart. Now, you can see that for the inner electrons, there's nothing pushing them away from the nucleus. In fact, if anything, there's stuff just pushing it towards the nucleus. So the inner electrons feel the full force of the nucleus. So these electrons right here, there's nothing between them and the nucleus. So they feel the full attractive force of the nucleus. However, for the electrons on the outside, those electrons feel both an attraction to the nucleus, but also a repulsion from other electrons. And so I'm going to write that as attraction from nucleus minus repulsion from inner electrons. And when I do that difference in forces here, the result is what we call effective nuclear charge. Someone really wants to say hi. Here, say hi. There, are you happy? Yeah, okay, great. Yep, that's exactly what she wanted to do. She wanted to say hi, and now she left. Thanks, Maya. How do we define effective nuclear charge in terms of numbers that we can count so we can, like, gauge it? Because you can eyeball it by looking at the screen. However, it's not going to be super helpful that way. We need to actually have numbers. So here's how we're going to define it. Effective nuclear charge, Z effective, is equal to the number of protons, that's this one, minus any electrons that are closer to the nucleus than the electrons that you're looking at. Well, if I'm looking at valence electrons, which I am in this case, I'm just going to subtract out the number of core electrons. So in other words, if I have 5 protons pulling my electrons in, but there are 2 electrons closer to the nucleus than me, 2 of those electrons effectively shield out 2 protons worth of charge. Because I'm attracted to those protons, but I'm repelled by electrons with an equal amount of force. So in this circumstance shown on the screen here, my Z effective would be, I have a charge of 5 in the nucleus minus the 2 electrons circled in the red. The outer electrons feel a force of 3 protons pulling on them. You can calculate Z effective for any atom you want to. And in fact, we're going to do that for a bunch of atoms. I got to clear all that off the screen here. Okay. So, depending on where electrons reside relative to other electrons, they will feel different amounts of charge. So, shown on this screen here, you can calculate that Z effective would be, you can see what the answer is right there, but if it's lithium, there are 3 protons in the nucleus. For my valence electron right here, there are 2 electrons that are closer to the nucleus, pushing it away. That's my effective nuclear charge. And so the electrons that are closer to the nucleus, in other words, all the core electrons, engage an effect that we call shielding. You might also hear this called screening. Core electrons screen or shield the nucleus from outside electrons. Sorry, meowing cat can't actually focus. So if we are calculating the effect of electrons on the outside relative to the nucleus, knowing what Z effective is helps us understand various properties that will involve charge. For example, atomic radius. So if we can calculate Z effective and then go back to that chart that we had right here, there it is, we might be able to observe a trend. In fact, you might have noticed that for lithium, I counted Z effective was +1, or 1 plus, I guess. But for boron, I got that. What do you notice about the sizes? Well, the one with Z effective +1 is much larger relative to the one with Z effective +3. And in fact, if I did this for beryllium, I would get that. And if I did this for carbon, I would get that. And so on and so forth until I get to neon. And so you can clearly see that as Z effective increases, the atom gets smaller. What we just need to do is actually do more calculations to show that this is actually what's happening that we're describing. So again, there's our formula for Z effective. Z effective is whatever the atomic number is, that's Z, minus the number of core electrons between the valence shell and the nucleus. This is why we did those exercises when we were writing electron configurations of underline the valence electrons and circle the core electrons, or whatever it is that we did. Because if you know which ones are which, you can then compute this equation. That's going to be important later on when we talk about transition metals in this section, because transition metals all roughly have the same size, more or less. And that's weird. You look at the periodic table and you would think, well, they shouldn't all be the same size. They should be decreasing, right? And it turns out that they decrease much, much, much more slowly because they all have the same Z effective, like we described earlier, with how many valence electrons they all have. And so that's going to be really cool. All right, so let's determine Z effective for chlorine. So Z effective equals the number of protons. Chlorine is 17 protons. minus the number of core electrons that are shielding the nucleus. Well, in order to determine that, I would need to write out its electron configuration, wouldn't I? And we should all be able to do that. There's chlorine's electron configuration. The valence electrons are in the highest end, so these are valence. These are core. How many core electrons do I have? 6 plus 2 plus 2. My core electrons are the screening or shielding electrons. So I go like this. And there's the effective for chlorine. So you can calculate Z effective if you can determine which electrons in your electron configuration are core electrons. And everybody knows the atomic number, so this should be a very simple calculation to do. All right, let's do another one. Let's do. Oh, we already did boron. Well, then we're gonna erase this, and we're gonna pick nitrogen. So Z effective for nitrogen would be. I should probably put the formula on the board, shouldn't I? So what's the atomic number for nitrogen? Well, it's 7. How many shielding electrons are there? Well, we got to write out nitrogen's electron configuration. Now let's do an oganesson. It turns out that it's not actually that hard for really big elements. There are my valence electrons. Here are my core electrons. So I'm going to put those up there. And there's the effective for nitrogen. What? Oh, sorry. The number on the screen here is the effective for boron, which is the problem we just did, or we skipped. So it's like, what? That number doesn't match. So for nitrogen, it's 5, but for boron, it's 3. So we'll just cover that up. Now, there is absolutely a pattern here. And you might notice that the pattern is... What's the ones digit in the group that you're looking at? At least for elements in groups 1, 2, and 13 through 18. And that's totally it. Any element in group 13, you're going to get a Z effective of 3. Any element in group 18 that isn't helium, you're going to get a Z effective of 8. Any element in group 2, you're going to get a Z effective of 2. And it's always 2. Transition metals are a little weird. You usually get 2 for Z effective. Now, since we can observe this, we can calculate Z effective for anything. Now I can go back to this chart. And we can observe the trend here. As Z effective increases, size decreases. Let's correlate that to movement on the periodic table. As you move down a group, radius increases because N increases. And as you move across a period, radius decreases because Z effective increases. Now, there will be minor hiccups with transition metals. For example, these are all roughly the same size. How do we explain this? These are roughly the same size too. In fact, they tend to increase at the end there. But on average, they're about the same size. How do we explain those trends? Well, if you calculate Z effective for any transition metal, you get an interesting result. So let's do that. So if I look at scandium and titanium, so if I write the electron configuration for scandium, I get that. And if I write the electron configuration for titanium, I get that. So let's calculate Z effective for each of these. So Z effective would be Z minus core electrons. So Z for scandium is 21 minus the number of core electrons. Well, how many valence electrons are there in scandium? These are the valence electrons. That means everything else is core electrons. So 19 of the electrons are core electrons. How about for titanium? What result am I going to get here? Well, Z for titanium is 22. How many core electrons are there? Well, if these are my valence electrons, then the rest of these are core electrons. And what do you know? You get the same answer. So when we look at transition metals, what ends up happening is that we're slowly adding more electrons, but the force they feel on the nucleus is the same. And electrons do tend to repel, so as you get more and more and more of them, the size tends to decelerate its downward trend. And you can see that up above, that as we add more electrons, the atoms tend to decrease in size less and less and less until they start to reverse that trend. And then we get to the group 13, where Z effective increases, and the radius goes back to decreasing rapidly. So that pretty much explains the entire chart for atomic size. Going down the periodic table and increasing the period number, atoms get bigger because N increases. Going left to right across the period itself, as Z effective increases, atoms get smaller in size. Transition metals tend to have roughly the same Z effective, so they have roughly the same size. Now, if you want more resolution in your transition metals, you can do something called Slater's rules, which takes the equation for Z effective and modifies core electrons to have weights. So here, I'm just using all the electrons have the same weight. A 1s electron is going to shield as effectively as a 3d electron. In reality, that's not true. 3d electrons are not very good at shielding the 4s layer, because 3d electrons are not very close to the nucleus. Like, they're very far away. They're roughly the same distance as the 4s electrons. So they get a lower weight to them. S electrons, however, are very effective, so they get a higher weight, and so on and so forth. And so what Slater's rules do is they say, okay, for every S electron multiplied by this number, every P electron multiplied by this number, da 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 da, now calculate Z effective. You get a different number, and that allows us to sort these a little more effectively, because they aren't all really Z effective equals 2. In reality, they do not have exactly the same force. They have close to the same force, though. For our purposes, we're not going to do that. We're going to use this formula. We're going to treat every electron as 1 electron as opposed to like 0.8 or 1.2 or whatever, to answer any questions that we might have about periodic trends here. All right. Now, this discussion on this slide is going to talk a little bit about Z effective and atoms getting smaller, and also a new topic. We're going to talk about ionization energy. This is actually going to come up in the next section, so we're going to see it later today. But let's introduce this to you right now. The ionization energy of an atom is how much energy is required to remove its electron. Electrons are attracted to the nucleus. They don't want to be removed, despite what you might have seen in 140, where we drop elements into water and they explode or whatever. You might think, oh, well, they must just be giving away their electrons for free. It turns out you still need to put energy in to cause the reaction to occur. All atoms need to be put some energy into them in order to ionize. For instance, here is the ionization energy for hydrogen. The attraction of the proton to the electron of hydrogen is 1.3 megajoules per mole. That's pretty powerful for a single proton. If I were to have a mole of hydrogen and I wanted to take out all the electrons, I would need to put in 1,312 kilojoules per mole. What if I want to do that for helium, though? Holy crap, is it way harder to do that. It takes almost 4 times as much energy to do that. Now, how do we explain these numbers in terms of Z effective? Well, for hydrogen, Z effective is just 1 because there's 1 proton. For helium, Z effective is 2. So helium's nucleus is pulling twice as strongly on the electrons than hydrogen can. And as a result of that, those electrons actually get closer to the nucleus. So then when we go over to this, not only has this gone up by a factor of 2, because it went from 1 to 2, this is decreased. And so this number ends up being way larger as a result. So these are just some actual data points so that you can see the effects of Z effective as well as radius. Oops. So this slide just goes over that reason. We calculated Z effective. Z effective for helium is larger than the Z effective for hydrogen. It's harder to pull an electron from something that has a positive 2 force than it does from a positive 1 force. So it's harder to ionize helium. It requires more energy. And then likewise right here, this talks about the effect on radius. Something that has a force of 2 plus pulling on it is going to have a smaller radius. Put those two things together, and you will get a smaller atom that is harder to ionize. We're not going to care so much about ionization energy yet, but do remember this discussion that we had just now, because it'll come back later today. The end result, and hopefully that's clear by now, is within the same sublevel, or even within the same N, the atom with the larger Z effective is the smaller atom. All right, so I'm going to give you two atoms. I'm going to give you lithium and beryllium. I want you to calculate Z effective for each one, and then tell me which atom is the smaller of the two atoms. Go ahead and do the calculation for Z effective. Type your answer in the chat. We'll go over the answer in about 3 minutes. One more minute, we'll go over the answers. All right, let's go over the answer here. So for lithium, C effective would be stop meowing at me. I have a cat that's just going meow, 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 and I just stop. My brain just locks up. I have a charge of 3 plus in the nucleus, minus how many core electrons there are. Well, for lithium, the electron configuration is 1s2, 2s1. There's my valence electron. There's my core electrons. And then we'll do the same thing for beryllium. So same equation, but there's my valence electrons, same core electrons. Different Z effective. So beryllium has a Z effective of 2+, lithium has a Z effective of 1+. Which atom is smaller? The one with the bigger Z effective. And there you go. Because its Z effective is larger, it is a smaller atom relative to lithium. All right. How about for oxygen or nitrogen? Calculate Z effective and type your answer in the chat. We'll go over the answer in about 2 minutes. One more minute, we'll go over the answer. All right, so let's calculate Z effective for each of these. So for oxygen here, and I'm just going to write out its electron configuration to start here. Z effective is, well, it's element number 8 minus the number of shielding electrons, that's these two, and there's its Z effective. There's nitrogen. It has a proton count of 7 in the nucleus. There's my 2 screening electrons. There's its Z effective. Now, be careful about what the question is asking for. Which atom is larger? So, the larger atom has the smaller Z effective. Therefore, nitrogen is larger than oxygen. Because we've been talking about, oh, which one's the smaller atom the entire time, and then all I do is say, oh, which one's bigger? And if your brain is on autopilot, like mine is 99% of the time, you pick the thing that we've been picking all along, you get the wrong answer because I didn't ask you for that. So, good for you on not getting caught up in that, because that is one way that I can check to see if you're really reading and comprehending the question. So be careful. And I lost my cursor. Where's my cursor? There it is. All right, cool. We are due for a break. So when we come back, we're going to talk about how ions change size when you remove electrons and how that affects Z effective. Because remember, Z effective is calculated for valence electrons. But what happens if you remove the valence shell? Well, we'll see what happens in just a bit. So please enjoy a 10-minute break. And when we come back, more of this. Alright, we're back. So what do we got next? We are going to talk about ions and how their Z effective can be used to calculate how big they are. Now, if I am looking at lithium, for example, so I'm going to write out let's look at these numbers right here. Let's look at lithium. I'm going to write out its electron configuration. On the left, I have an electron in the 2s orbital, but on the right, I only have an electron in the 1s orbital. 2 electrons in the 1s orbital, actually. So let's just indicate that. We'll do that. All right. If I wanted to calculate Z effective for regular old lithium, that would be 3 plus. Here's my shielding electrons. 1 plus. No big deal, right? We've done that enough times today. But what changes if I do this? Well, first, the electron configuration becomes 1s2, and that's it, right? Because I stripped away this electron. Then when I go to calculate Z effective, there are no more core electrons. There are only valence electrons. So when you get rid of the entire valence shell, Z effective tends to go way up because you have a whole new layer that is now the valence shell, and there are much fewer core electrons. Let's look at sodium as an example here, because you'll notice that the size for sodium goes way down as well. So if I have sodium here, if I calculated Z effective, here are all my core electrons. Sodium has 11 protons, minus the 10 electrons there. There's its Z effective. But if I do this for sodium plus, I get rid of that electron on sodium plus. This is now my number of core electrons. And holy crap, it's way larger, right? Because I just lost 8 screening electrons. They are now the core electrons. So you can see that the size changes proportionally. Now, does it decrease by a factor of 9? No, not really, because... Excuse me, sorry, I'm just taking a drink of water here. It does not decrease by a factor of 9. What it does do is, relative to other things that have the same number of protons and electrons, it would be smaller because there are more protons in the nucleus, pulling those electrons closer and closer and closer. But you can see that, oh, okay, well, Z effective is bigger. This must be smaller than relative to the original size it had. And sure enough, it is. So the trend that we observe is that cations get way smaller when you strip away electrons. Not only are you removing a valence shell completely, but the electrons that remain feel a much higher Z effective. Oops. Now, what about the reverse process for making anions here? Well, when you add electrons, their size increases very quickly, but it's not because of Z effective. Because if I'm adding electrons in here, regardless of whether I have O or O2 minus, you should be able to calculate that Z effective for these is the same thing. So how the heck do we explain this? If they have the same Z effective, shouldn't they have the same size? Well, no. Oops, hold on. I made a mistake here. This shouldn't be a 4. This should be a 6. Well, no, they shouldn't have the same size. What ends up happening is if I have this force in the nucleus pulling my electrons in, they will be some distance. But now if I change nothing in the nucleus and add 2 extra electrons, I have to spread that same force over 6 things now. So now these are allowed to get further away, because I can only hold on to them like 80% as effectively, because now I have to divide my attention among 2 extra electrons. You could think of like walking dogs at the dog park. If you have 2 dogs and you let them go off of their leash and run around, that's way easier for one of you to watch 2 dogs than it is for one of you to watch 12 dogs. Electrons are the same way. They're just yappy puppies. They will just take off, and you have to be very attentive of them. But the more electrons there are, the less attention you can pay to each of them. So as we add electrons to form anions get much, much larger. And the reason for that is because Z effective remains constant, but you have to divide that effective nuclear charge across more electrons. The other reason that can be used to support this is that electrons repel each other. And if you're cramming extra electrons into the space, so if I'm adding these electrons into that orbit, or the orbital, I'm going to need more space for them to occupy, because they will repel each other, and they will push each other away. Alright, so you don't need to know the numbers, you just need to know electrons are like yappy dogs. That is what you need to know, yes. All you need to know from this slide is that ions change size relative to their neutral atoms. Cations get smaller, anions get larger. This right here is just the series of atoms, what is called the isoelectronic series. The isoelectronic series is just any group of atoms that have all the same number of electrons. That's why they're isoelectronic. If we were to calculate Z effective for these in the isoelectronic series, what we would see, and I'll leave this exercise to you if you want to calculate these. These are the Z effectives that we calculate. Remember that for things like potassium and calcium, Z effective is way higher because normally it'd be 1 or 2, but then I strip away the entire valence layer by removing those electrons. The next one down becomes the valence layer, and that's how you get these calculations. What you see is that if I correlate Z effective to size, as Z effective increases, size decreases, which is what we would expect. And so this is where that sodium thing came in earlier that I kind of bumbled what I was talking about. I was like, oh, what's the term? I couldn't think of it. I was thinking of this. So if you compare sodium plus to other things with 10 electrons, then you'll see a much more obvious trend in sizes. So like if you compare it to neon, it'll actually be just slightly smaller than neon. All right, so what I want you to do I have more of these on here? Yeah, I do. Okay. What I want you to do is, using quantum mechanics and Z effective, so whenever I say using quantum mechanics, really what I mean is using this. And also Z effective. So this is quantum mechanics, those two things. I want to use those two things to tell me which atom in each pair is the smaller atom, and which ion in each pair is the smaller entity. Also, which electron is they are... Sorry, I was trying to read the statement that was on here. Don't we write ions as negative so they aren't such big numbers? I'm not sure what you mean by that. Anyway, answer these two sets of questions. We'll go over the answers in just a bit. 2 more minutes and we'll go over the answers. All right, let's go over the answers here. So, what I like to do when I do these types of problems is I like to set up something that looks kind of like this. So, since you're going to get a lot of questions about things like atomic size, and then next we're going to do ionization energy, and then we're going to do electron affinity after that. If I'm looking at two things, first I write them down, and then I make a little grid out of it. Like this. So if I want to look at the maximum N on magnesium, so it's in period 3, so the highest N would be 3. What is magnesium Z effective? You can calculate that by now, I hope. Then we'll go to calcium. Calcium is in period 4, so it has a higher N, and its Z effective is also 2. And so now the question is, which is smaller? Well, whichever one has the smaller N must be the smaller atom. So, there you go. All right, let's do the next one. Chlorine and argon. So we got chlorine and argon. Oops. N Z effective. So what is N for chlorine? Well, it's in period 3, so it's 3. What's the effective for chlorine? 7. Argon is also in period 3, so it has N equals 3, and Z effective is 8. Which is smaller? Well, within the same level, larger Z effective, smaller atom. So argon must be smaller than chlorine. And then finally, we can look at sulfur and oxygen. So sulfur is in period 3, and its Z effective is 6. Oxygen is in period 2, and its Z effective is 6. Oops. And then larger N. Oh, we want smaller. Sorry. And so there you go. So this must be the smaller atom because it has a smaller N. They have the same Z effective. All right, so there's the first 3. Even though we haven't really talked about N very much here, we did mention it at the beginning, though. Don't forget that N exists, because N affects size just as much as Z effective does in terms of its importance. And if you have the same Z effective, you have the same strength pulling from the nucleus, and therefore that won't be a factor. So if you have 2 atoms or ions with the same Z effective, you can't use Z effective as your deciding factor because it's the same Z effective. They are the same attraction. I can do the same thing here. So calcium is period 4 and its Z effective is 2+. But if I make it calcium 2+, now there's only 3 layers of electrons because I stripped off the topmost one. And the Z effective for those electrons in the valence shell becomes this. And this is very obviously smaller. For iodine and iodide, you'll notice that when you do this table, you kind of don't get anything out of it. And that's actually useful information, it turns out. So they both have N equals 5, and they both have Z effective 7+. And so you might just draw no conclusion. Well, if they have the same Z effective, you could say, oh, more electrons for same Z effective, which means that it is larger. Well, the question is asking us which one is smaller, so this one's smaller. Oh, I should be more specific here. Specifically, more valence electrons. Technically, it doesn't matter that I say valence electrons there, but probably I should just say that just to make it more clear for you guys. And then finally, for argon and chlorine, or chloride, actually. Oops, sorry, I had them backwards where I was in my head here. All right, which one is smaller? Well, bigger Z effective means smaller ion. All right. Those are our trends for atomic size. Lot to take in there, I realize. But the goal of this whole discussion, of this whole section that we're doing today, and then a little bit more of on Tuesday, is that the 2 things that we care about are how far away the electrons are, which is N, that's the radius part of the Coulomb's law equation, and then Z effective. What is the effective nuclear charge that the electrons feel? That's the Q part. Any questions, let me know. We're going to return to first ionization energy because I'm going to show you a chart of ionization energies here. We're now going to try and predict how we can tell how much energy something will take to remove its electron. And you'll see that the trend is sort of like the inverse of size. However, there are some discrepancies. So let's first let's define ionization energy in a little more specific terms. The first ionization energy is the amount of energy to remove the first electron on an atom. Most atoms have more than one electron, so you can take the second one and it will have a second ionization energy. And you can do this forever and ever and ever until there are no more electrons. Now, every time you pull an electron away, it gets harder and harder and harder to pull the remaining one because the Z effective that those electrons feel on the valence layer is now being concentrated on fewer electrons. Just like our puppy analogy, if you're watching 6 puppies and they're all going all over the place and then someone, like the owner, comes to pick up 4 of them, now you only have to watch 2, so you can watch those 2 with more attention. They're not getting away. Same thing with electrons. If the first one gets taken, now you focus on the second one, and that one is held more strongly. If you keep doing that, though, you might end up removing all the valence electrons, and that will change your Z effective. And we're going to show that in a second, what the impact of that is on ionization energy. Ionization energy is always positive. Otherwise, ions would form spontaneously on their own. All matter would exist as an ion. So therefore, you must have to put in some energy in order to remove electrons from a nucleus. All right. We're going to do the same thing that we did with size. We're going to look at these 2 terms. What do you notice happens to energy needed to remove an electron as size increases? So for N, here's how much energy I need to take away for hydrogen. And then we've got lithium, then we got sodium, then we got potassium. And you've probably noticed that, oh, it's getting lower and lower and lower and lower. And I'm not trying to show that these are whatever distance apart. I'm just showing that they are lower, even though I can't draw straight lines. So the ionization energy of the first element in each period is lower than the preceding first element in the preceding period. However, as you go across a period, it gets harder and harder and harder to ionize things, with some exceptions. And then we see the flat transition metals area again. So obviously Z effective has a role in this. So you can see the following. As N increases, ionization energy, the first ionization energy specifically, decreases. It gets easier and easier to ionize things because the electrons are further from the nucleus. R is larger. Therefore, the energy of attraction between that electron and the nucleus is reduced. What about Z effective? As Z effective increases, the ionization energy of your atom you're looking at increases. And you can see that right here. So lithium has a Z effective of 1. And it increases as we go across the trend, although there are some weird things going on here. So, for instance, what the heck's going on here and here? Well, we can explain those using quantum mechanics, believe it or not. That's kind of the point, right? All right, so we're going to just look at this trend right here. All right. And you know what we're going to do? Hold on just a second here. We're going to open this guy up again. We're going to see if we can use this to explain my trends. So for the element with 2+, that's beryllium. So if I were to write out beryllium's electron configuration, that would be this. I'm not writing on the right layer. I'm not going to save it anyway. That's okay. There's beryllium. And then the third one would be boron. All right. So this is Z effective 2+ and 3+. All right. However, the ionization energy of boron is lower than that of beryllium, and we would expect it to be the other way around. Well, let's fill in the electron configuration and see if we notice anything cool. That's not helpful. Actually, you know what? We'll just do that. Sorry, I was trying to get another layer to write on. So for beryllium, we would do this. 1, 2, 3, 4. There's beryllium. But for boron, it's like this. Now, what is ionization in terms of this diagram? Well, if I go all the way up to the top of the diagram, ionization energy is basically getting an electron from wherever it is all the way up to n equals infinity. How much energy does it take to do that? Well, it takes this much, right? So that's how much it takes for beryllium. But what about for boron? All right, so we'll put beryllium back. Now I'm going to put boron in. Whoop. Why does boron take less energy? Well, the 2p orbital is higher in energy than the 2s orbital. So what you are observing on the PowerPoint slide graph here, right here, this is the transition from S to P. So when you go from 2s to 2p, your electrons go in a higher energy orbital. That energy means that that electron is further from the nucleus, and thus it is easier to ionize. So that explains the first transition. What about this next transition? So first let me clear this. Oh, I don't want to do it that way though. Boop. Okay. And then we'll clear this one. And we're going to look at the transition from the 5th one to the 6th one. So 5+ would be nitrogen. So nitrogen is this. 3, 5, 7. Yeah, that's right. And then oxygen is this. And then we have Z effective of 5 and 6. Make it a little bigger so we can see it. All right, so I'm going to draw in nitrogen. 3, 4, 5, 6, 7. There's my nitrogen. And then in a different color, I'm going to add in the next electron for oxygen. What could cause ionization energy on oxygen to be slightly easier to ionize? In other words, it takes less energy to ionize oxygen relative to nitrogen. And I realize I'm talking from either the past or slightly in the future for anyone who's watching the lecture, and you're looking at this and going, oh, look at that, they're paired. Those two electrons don't want to be together. They push each other apart. And yeah, they do. One electron repels the other electron in its orbital away, and that gives it just a little boost to make this ionization easier. So on the chart here, what we are seeing when we go from 5 to 6 is the first time that an electron is paired in an orbital. And so you could see this trend occurring over and over and over on this chart. When you go from 2 plus to 3 plus, you go from S to P. And then when you go from 5 plus to 6 plus, you pair an electron in the orbital the first time. Now you might ask yourself, well, wait a second, why does it only go down for the first paired electron? And in reality, it's going down for all of them, because this is where the trend would be if it were not for the effects of electron-electron repulsion, which is what this is right here. Same thing is happening for the transition from S to P. The P effectively lowers the line down a little bit. Otherwise, this would be a straight line. This we don't really need to talk about because we already said that Z effective is roughly a constant, and since that's what's affecting ionization energy, all of those ionization energies for transition metals are roughly constant. Again, the granularity comes from Slater's rules, which we'll talk about in 361. Not we, but the royal we. All right, that explains ionization energy. So it doesn't seem like there's much there because we've done all the discussion on atomic radius already. But there is a lot going on here. So be very careful about learning the trends for ionization energy relative to N and Z effective. And you can see those at the top here. So as N increases, ionization energy decreases. As Z effective increases, ionization energy also increases. And then we've got the S to P transition, which causes these little boops, we'll call them. And then the first time we pair electrons in an orbital causes another boop. All right, so now we are ready to answer questions about ionization energy. So, which atom has a higher ionization energy? Oxygen or sulfur? Which one is easier to remove an electron from? Do the little N and Z effective grid, just like I was showing you in the exercises before, because that'll help you here. And then type your answer in the chat. We'll go over the answers in just a bit. All right, let's go over the answers here. So if I compare ends, oxygen has N equals 2, S has N equals 3. If we compare Z effectives, they're both 6+. Which is a higher ionization energy? Which one is harder to take an electron from? Well, as the electrons get further away, which is what N is telling us, they get easier to take. So I want the one that is harder to take, and that's this one. So I would say oxygen is smaller. Electrons are closer to nucleus. Nucleus, and harder to remove. All right, how about for this pair? Also, that's totally an emoticon right there. Woo. Haha, you can't unsee it. Which has a higher ionization energy? Phosphorus or germanium? Give you 2 minutes to puzzle it out. We'll go over the answers together in a second. All right, let's go over the answers. Phosphorus is the correct answer. Very good. Let's show why that is. So if I look at the highest N, for phosphorus, that's 3, and for germanium, that's 4. And if I look at Z effective, germanium's Z effective is 4+, and phosphorus's is 5+. Now you might be thinking, oh crap, they're both different, but it turns out both of these work towards higher ionization energy. So higher Z effective means stronger pull from the nucleus, and that ionization energy increases. And then a lower N means ionization energy increases as well, so obviously the winner is phosphorus. It wins both categories. Now, you'll notice that on the periodic table, phosphorus and germanium are diagonally across from each other, where phosphorus is further up and to the right. If I gave you a pair where you had a diagonal and one was further up and to the left, you would have opposite issues. One of these atoms would have a higher N, and one would have a higher Z effective. And you wouldn't be able to determine the answer. So I might give you one of those on like the sample problems coming up. Let me look and see if I do that. Yeah, I do totally do that. It's this one right here. So do the exercise anyway, and you're going to notice that like, oh, I can't determine this, and we'll talk about what that means. But for the other three, it is solvable. So tell me the higher ionization energy in each of the three pairs. We'll go over the answers, and then I guess we're done for the day. So I'll give you 3 minutes to do this, because we're out of time. One more minute, we'll go over the answers. All right. So for lithium and sodium here, lithium is a smaller atom. It only goes to n equals 2. Sodium goes to n equals 3, but they both have Z effective 1 plus. Which is the higher ionization energy? It's harder to ionize something that's smaller, so lithium is the winner. All right, let's clear that, and we'll do it again. So for rubidium and strontium, they're both in the same period, which is n equals 5. Rubidium only has the effective 1 plus, and strontium has the effective 2 plus. It's harder to pull against 2 plus, so it's harder to ionize strontium. All right, let's look at iodine and selenium here. Iodine is in period 5. Selenium is in period 4. But iodine is a 7 plus Z effective, and selenium is a 6 plus. Now, it's harder to pull an electron off of something with a higher Z effective. But it's also harder to pull an electron off of something that is smaller. And so for this reason, we can't really conclude, based on trends, which one is going to be easier to ionize. Or harder to ionize, or whatever. So if I give you a pair that are diagonal top left, bottom right like that, then you won't be able to determine the answer. And that's the answer, is impossible to determine. Finally, for fluorine and sulfur here, this goes in the other diagonal. Fluorine is smaller at n equals 2. Sulfur is at n equals 3. Fluorine has a 7 plus effective nuclear charge, and sulfur is 6 plus. It is harder to pull from both a bigger Z effective and a smaller N, so fluorine is by far harder to ionize. All right, that's ionization energy. When we come back, we're going to talk about second ionization energy. We've already talked about these exceptions here, so I'm going to just skip over these two slides here, and we'll talk about ionization energy 2 and beyond at the next lecture. Now, next week is week 8. There is a box on there that says, hey, we could use Monday as an extra lecture. I'm actually going to elect to do that. So extra lecture on Monday, which would be the 24th. And the reason I'm going to do that is because I actually don't have any more weeks that I can do this, I realize. Because week 9 is Memorial Day. We're not having a lecture on Memorial Day. And week 10 is an exam week. So you have two exams now. You have 2 lectures already, and then a review session on Wednesday. So I am going to use Monday of week 8 to do an extra lecture, just so that we can be sure that we are done with Chapter 3 on Tuesday, and we can start Chapter 4. And then Chapter 4 is more or less the last chapter. You could effectively put Chapter 5 in Chapter 4. Chapter 5 takes like an hour to do. For some reason, that's how they split it. So please be aware of that. Also, please be aware lab worksheet number 3 is closes tonight. Make sure that that is in by the deadline. And otherwise, I wish you a happy and productive weekend. Go out and enjoy the sun. It looks like it's really nice out there. At least right now. Sorry, I'm still trying to find the music here. There we go. And have a great weekend. Make sure you practice the quantum mechanics, because this quiz is going to be rough. Take care.